GM Hashheads. GM Hashheads. Shenkui. Aloha. Aloha. Habibi. Habibi. Arigato mas. And everything. What did I forget? Chinamanen. Chinamanen. Good day, mate. That's the funniest one. Good day, mate. How you doing, Hashheads? I hope you're fine. We have a lot to cover. Good to see so many celebrities in the chat. We have a lot to cover today, so I'm gonna go straight to the meat. I guess this is the story about how we created the 3CDVS is here, Joseph is here. We have backups, guys. We have the professionals with us today. I guess this is the story how we made a proof of work chain, or how Jack made a proof of work chain within 2 weeks, and a huge amount of engagement from and with the community in the name of innovation, research, education. So I'm very happy to hear and see everyone's excitement to learn and also to teach others. We make research and we invite you to do practical research with us. And the alternative is to do it behind closed doors. But we do open source. We learn together. And I've talked about this a lot, that I think that many L1s are suffering in the long term with the design decisions they've made in the past. And I've talked about that in terms of tokenomics. But this is also true for the tech. Mad Mike, can you say a swear word when you do a Tourette click once? Je bent i mig kuteve. There, I did it. And this is also true for the tech. But a lot has happened in the space since Bitcoin, and we can learn from what has worked very well and what has not worked, and also explore possible capabilities, merging capabilities to learn. So the creation of X1. While we're doing this, now is the time that we really deep dive into these consensus and value-making systems. And we're working on an updated fastnet with our own customization of that proof of stake DAG chain, as you know. And simultaneously, we study other systems and play with their models, as we're doing now. So we are building infrastructure that both needs to work decades from now, but also needs to be flexible and adopt the very best tech. So we're not only building a currency with Zen and a chain with X1, we're building a whole universe with the same theme of censorship resistance, immutable systems, trustless systems, where participants can have self-custody of their funds. And I think that's very important. So we have Zen, we're making X1, we're tackling Bitcoin bridging, we're soon ready to release early version of Zen GTP. We do horizontal scaling and a bunch of other things, all following the same armada of power tech that collectively makes us very strong and able to do whatever we want. And for everyone who participates in the system. So community gathered around this proof of work, of learning proof of work stuff, which is very cool to see. This knowledge sharing that we also have in the community in terms of engagement and educating each other. There's over 1,000 messages every morning in the chats. Hand up, who got sleep this past 2 weeks? I hardly got anything. It's just been nuts. And people are helping each other. We're learning together. It's amazing. We just discovered we have a huge resource in the community who have been doing open source stuff for more than 30 years, who know about coding and servers and open source hardware. And these are very great assets that we have in this community. So if we can have proof of work, know-how in the community and utilize that engine as well, it's great. Many people are clearly obsessed with this. I'm not going to mention any names, Joseph and Tracy the West. So we're building things together. It's not about analyzing prices, swing highs, swing lows. It's not about team building behind closed doors. We're doing it in the open. We test theories in practice, and we learn from what we do. We go from clarity with empirical data and see what works. And that's a superior approach, I think. And XenBlocks is a perfect example of this, because XenBlocks is a practical experiment in value creation, consensus, and systems building. It's a study in cryptography. It's a perfect example of how a chain works in the most simple form. And here we can use various resources. We can be more available to make. We can make tech like this available to anyone, proof of work available to anyone, and by lowering the barriers for you to participate in the block production, in the block production. So and we can make it harder for other stuff that are less beneficial to have in the systems, like ASICs, for instance. So this XenBlocks is based on a proof of work. It is proof of work at its base, and it's based on a cryptographic hash algorithm called Argon 2. But we can mutate this chain into become a proof of work, proof of stake hybrid as well, which is very interesting. So I'm going to talk about that too. So this has come very sudden and exploded in engagement, which is just nuts. So today I've tried to map out all the individual components of this to somehow try to make sense of it. It's a lot, I will warn you, it's a lot to take in, but I just have to deliver it to you, and then we will see what sticks and what doesn't stick. So there will be a lot of theory today, and because we get so many questions about how this stuff works. And I'm learning a lot too, to be honest. I've learned super much in the last 2 weeks about this. It's been super fun. So I want everyone to participate and try this. So XenBlocks, let's go down to the meat. This is what I will cover today. So first, we're going to have some fun and just start mining, because that's what is the best thing, that you guys just see how easy it is to really participate and mine XenBlocks. It's new for a lot of people, and there's language and code and terminals that you never interacted with in many cases. It's a lot of confusion, a lot of frustration. That frustration is good, because it means you're thinking, you're learning. So embrace it and ask questions and go to the chats. And we have awesome people. Crypto Bro is in the house too. Good to see you. Jack Levin is here also. Thank you, Mike. Thank you, Mike. Yeah. So we're going to start with that. But if you just get over those hurdles, and the hurdles aren't that many, you will really feel like Neo in Matrix and do cool stuff. And then we're going to talk about all the individual components. We're going to talk about what Hashrate is, Leaderboard, the difficulty adjustment mechanism, which is an important part in this whole proof of work concept, the mempool, the state, the blockchain, sync node, how we can decentralize the chain and verify the transaction and build the blocks. We're going to have an overview of the whole process. We're going to talk about block voting, some terminology, sort that out. Merkle trees is very important to understand. And then we'll talk about proof of work versus proof of stake. What are the really differences there? And there's different theories about how you can have hybrid consensus, and the approach that we are taking with XenBlocks when it comes to this. And then talk a little bit about the community aspect of all of this too. So TPX just made this. It's live in Wall Street right now. XenBlocks, mine crypto with your CPU. It's super cool. So yeah, guys, let's go down to the meat. Let's go down to the meat as we always do. So this is like an overall process of what you need to do to get started, and it will differ a lot depending on some stuff. But this is true for everything. So the first you need to do is to log into your server with your terminal, or open your computer machine. So on a Mac, a terminal looks like this, if you didn't know. And on a PC, on a Windows, I don't care how it looks like, but it looks similar to that. So the first thing we need to do once we know which environment we're going to mine from, if it's a rented server or from your computer, both are fine, is to run the update command. So it's packages that index. It's a database that stores the list of software packages from the repository, from the repo. So we need to do that first, and then we need to download the repo or clone it from Jack's GitHub. So we're going to do that as well. And then we need to install Python 3, which is super awesome language. It's super simple. And I mean, it's not simple, but it's like comparatively super simple. And then we're going to go into the directory where we have all of these files, and then we're going to install some requirements that's needed, especially the Argon 2 hash cryptographic algorithm that we need in order to mine. And then we're going to update with our own address. So when we mine, it gets to us. And then we're just going to run it. So that's what I'm going to show you now. And you can screenshot this, but this is basically the commands that you're using in terminal that I'm going to use now to start mine. And if you have Windows or wind blows, then you use this command to install Linux. So Linux is open source. This is also super good that we're starting to interact with Linux as an operating system. So let's enter the matrix. Let's enter the terminal. Is it this one? Bam. So here we have a new fresh terminal. And so the first thing we're going to do is to, oops, there we go. Yes. So go into another terminal, I guess. Now it's working. There we go. So the first thing we do is we do the app update. Bam. And that's going to run for a little bit, not too long. And then when that's done, we're just going to install the Python language. I think I already had it installed, but you just use this command, apt install Python 3-pip. And then we're going to clone the repository from Jack's GitHub. So we git clone and then the address where that GitHub is. smack, and then we're going to go into that directory. So now we are in that directory, and then we're going to install the requirements needed, Argon 2 and a bunch of other stuff. And then we need to go into the config file, nano config, and change to the address that we want to mine from. Where do I have my address? There. So we go into this file, and then you just go down and exchange this address to the one you want to mine from, and then you save that. And when we've done that, now we have installed Python, and we have cloned the GitHub. So now we have access to the miner. So what we can do now is just start mining. So here you can see that it's going to look like this. And now we're mining block 1, but it's going to adjust very soon. Here we go. Restarting mining round. So this is the, wow, the difficulty, guys. It's insane. It's 2,800 now. It's pretty nuts. But now we're mining XenBlocks and Zuni and SuperBlocks and Xenium. So this is pretty cool. But you see, it's not that many things you need to do. But you, like 95% of you are going to get stuck on the way on something. But just go in the chats and ask, depending on what you get stuck on. But there's a bunch of other stuff you can do too that's very helpful, because when you are mining, you're using your computer is working a lot. So it's working because it's trying to guess the right solution. I'm going to explain exactly how that works, but it's using a lot of your CPU. So what can be good to do is to go to, you just enter top, and then you can see your computer's CPU usage up here, how much it's using to mine. So that's very good. Another one which is very good to use is HTOP. So then you can see your instances that you have on your computer, how much they're working. So that's also a very good command to use. And what else? Yes, then we can run something called sync node. And this is how the network can become decentralized. And since everyone is syncing and verifying the blocks and building them to the state. So to do that, you just do this. Whoops. Sorry. So Python 3 sync code, and then your address that you want to sync to. So what it's doing now, it's fetching all the blocks from the state and syncing them. So you become a node basically by doing this. So you're downloading the whole database, and then once you've done that, you start syncing the chain. So once we've done that, we can also start interacting with the chain, with the state, with the blockchain, blockchain DB, and that's very cool, because then we can go in and analyze a lot of data and stuff like that. So another cool thing you can do is to use this command, for instance, because you can open many different terminals in your computer and start to mine on all of them. Or you can use cool commands like this one, where you start many of them at once. So now I just started 24 mining sessions on this one server, which is pretty cool. So if we go now to, for instance, if we go now to top to see our CPU, we can see that the CPU percentage is 95%, because it's using all the CPUs in the on the computer, all the instances. So that's pretty cool. So this top is very good to make sure that you want to utilize as much as possible of your CPU. So what I just showed you is basically let's go back and see that it's mining. Yeah, so we can let it mine for a while and let it be there. But what I just showed you, the rest when it comes to mining basically is customization for your particular environment. If you have a PC versus Mac, if you use Linux and Ubuntu, and more cool stuff like that. But this is the whole fundamental picture of how you mine, basically. So don't give up. Just try to understand step by step what it all means and what these steps really do. And if you get frustrated, as I said, it's just good. So I will now go into detail how all of this works and what the hell I'm doing and how it all relates to one another. So we'll let this one mine for a bit, and we go back to Miro. And you can also go here if you just want to try to mine from a browser. Then you're using your computer's CPU. So Zen miner. Let me post the address for you guys. Zen miner. Yeah, I'll just post it here too, so you see. Oh, super annoying. This is annoying with Miro. You have to like copy. If you try to post a link, it wants to give you this other command. There we go. So you can try that. You just connect your wallet and start minting. Yes. So let's talk about hash rate, because this is an important concept when it comes to proof of work. So and before we dive in more how XenBlocks works, hash rate is very fundamental. So in proof of work, the work you are proving that you did in order to be selected to make the block is solving this cryptographic puzzle of coming up with what the system considers to be the correct hash. So hash rate is a measure of computational power on a blockchain network. Hash rate is determined by how many guesses are made per second. So it's measured in hashes per second. The overall hash rate helps determine the security and mining difficulty of a blockchain network, you can say. So here's some example. Here we have the hash rate of the Bitcoin network, for instance. So as more miners join, the competition arises. It gets harder to create blocks, and the hash rate goes up. And here is ETH proof of work, for instance. So we can compare them as well as networks, and we can see that Bitcoin has 442 million tera hash per second, and ETH POW has 8.86 tera hash per second. So you can learn to use these units. And here is XenBlocks, and this is actually wrong. We've changed this now, and this is a key difference when it comes to how XenBlocks works, because we have a fixed global hash rate for everyone, and that's what makes it actually pretty cool. So in Bitcoin, what miners do, they use this hash algorithm called SHA-256 to produce a hash. and it takes data and it produces this 256-bit number, which is a summary, which is a fingerprint of that data. So when you put in data into the function, you can't predict what the fingerprint will look like. So the miners are putting the header of the block, they have a candidate block they're trying to solve or prove with the proof of work, and they take the header from that block, and what the header contains is the Merkle root of the transactions, which is a summary of all the transactions that are in a block. So it contains timestamps, it contains the hash of the previous block, the parent, so you know how it's connected to the chain, and all of this information is hashed together. So there's a special number in there also called a nonce, and that is selected randomly to introduce some randomness in that exercise. So if the hash that they are producing has a certain number, has a certain amount of zeros in the beginning, then they win. So they're trying to guess to get as many zeros as is needed. So then they have proved and solved the puzzle. But the chances of them having that number of zeros in the beginning is very, very, very small. So what the miners are then doing is they're hashing. So they're guessing to produce the result again and again and again and again. And it needs a certain amount of zeros in the beginning. So if they win, they will be selected to be the dealer, to produce the block and push it out to the network for verification of the network. And if the network accepts the solution, they win and they get the reward. So they have an upfront cost with the servers to do these mines and most of them using ASICs. And so that's how it. They are of course incentivized to do it correctly. Because that's the only way that they will get the reward. So in proof of work, generally speaking, hash rate is one of the most interesting metrics to analyze to determine how strong a network is. And why is it so? Because the bigger the hash rate, the harder it is for one single miner to influence the network in those kinds of networks. So now, XenBlocks. So what is really XenBlocks? The way we see it, it's a study in cryptography. How can you convert proof of work into tangible, useful assets? So ASICs, they are computer chips that most Bitcoin miners use to mine Bitcoin, but they're very energy intense. So Jack looked at the Bitcoin code and replaced the algorithm from SHA-256 to Argon-2 instead. XenBlocks is not a fork of anything. You can say that XenBlocks is running on a version of a Bitcoin miner that he changed the code on, but it's day one scripted by Jack himself. He wrote it on a weekend, basically the foundations. Oh shit, I've been muted. Where did I lost you guys? Yeah, they're censoring me. Okay. 2 minutes. Jesus. Okay. I restart from here then. I hope you heard this part. But basically, this was just the Bitcoin hash rate, and it's an important metric to determine the security of the network, you can say. But let's begin here. Sorry. Okay, Jack wrote it on a weekend. That's where I lost you. I don't know why it does that sometimes. Super annoying. Anyway, so yeah, where was I? Yeah, so what the script does, it does mining. So there's a difficulty factor and an extra difficulty for SuperBlocks, and more on that later. So what XenBlocks is a demonstration of simplicity of blockchain implementation, because you can argue that many blockchains are over-engineered. At least that's what Jack thinks. So for you to participate, you just need your time and electricity, basically. So it's like being Satoshi from day one, and how Bitcoin basically was set up from the beginning. So the goal of mining is for our community to explore the ability to mine XenBlocks and to mine with proof of work, and for us to get a lot of knowledge that we can leverage for X1. So miners, they're decentralized. They look for blocks the same way Bitcoin miners look for blocks. It's really the same tech there. But the miner is using this special encryption algorithm that's basically nobody's using, that is much stronger in some aspects, and that is ASICs. And I guess we can say that it's semi-GPU resistant as well. So we're going to talk about that. So similarly to mining Bitcoin, but much more simplified. With XenBlocks, you're mining, you're running a script on your computer, and you're also using this hashing algorithm to find the specific solution. But instead of zeros, as they look for in Bitcoin, you search for Zen 11. So it's like a digital treasure hunt. And the algorithm it's a fair mining algorithm. So with Bitcoin, mining is pretty much centralized. It's usually a group of 5 people who take all the blocks. So this eliminates ASICs and GPU mining to the most part. So everyone with a CPU can mine. So with your phone or PC or your computer, or someone even use their fridge to mine, which is pretty cool. And when you're mining on your computer or phone, it's using the CPU there that you have in that device. Which is not going to be as strong as a computer, but the point is that anyone can do it. So it's pretty cool. It's written entirely in Python, so it's very easy to understand. It teaches everyone what proof of mining is all about, but also how you can run command line, learn to interact with the terminal, and so on. So yeah. So let's look at how so to learn like how a blockchain really works. This is awesome project. So let's look at how the algorithm really works. So when you find a block, it looks like this. It's a bunch of data. That's just nonsense in the beginning. But let's break it down. So your computer with or server with CPU hashing is trying to find this hash that we have right here with Zen 11 in it. So each block is counted when your miner finds the sequence of 65 characters with Zen 11 in your hashes. So the server runs the algorithm and searches for this hash. So here we can see that I found a block with Zen 11 in it. So we can see first that it took 12 million attempts, so 12 million guesses for the computer to basically loop to find the correct solution. But we also have some other juicy data here. So we see here that it says Argon 2. So Argon 2 is the cryptographic hash algorithm used. 19, that stands for the version. M, that's the difficulty factor. So here it was 1,800. Right now it's 2,800. And T is just the number of times, and P is parallelism. It's not so important. Just focus on that they're 1 for now. And then we have the correct hash. But here is an important thing. This is the key. And that's a vital thing. So I just extracted this data here. So here we have a hash, and here we have the key. So this is really where cryptography comes in and how it's so beautiful. Because if the goal is to find a hash looking like this, then you might think, well, I can just come up with some random numbers and fake it and push it out to the nodes and they will accept it. No, you can't do that, because you must also present this key. So the key is produced by your hashing algorithm to prove that you really did the work to find the hash. Because even though you can fake the Zen11 hash, you can't fake it together with a corresponding key. So this is a key that's produced. It's matching the hash that I mined. The dashboard runs verification, and it will only insert my result if the key matches the hash I found. So this is what the validators are doing. And now I'm going to do a demo of this, which is actually pretty cool. So if we take this key and copy it, and then we go to I haven't slept in a day, guys. A bit tired, to be honest. And then we go to this page. So this is something I think you should try out once you find the block. This is the Argon 2 hash generator and verifier. I hear you fine. Awesome. So if we here paste the key that we found, and we input this inputs here. So we have Zen11. So this is the salt. Basically, it's just an added password to make it more secure. We have the parallelism factor. We have the memory cost, the minting difficulty, which we also saw in the block, right? And then we have the hash length. So if we generate a hash from this inputs, then we can see that we will find this hash with Zen11 in it. So it's pretty cool. And this should match the one that we have in the block. Because if I change anything here, like just one symbol, one character, this to this, then it's going to create a completely different hash. So they really need to match like 100%. So Argon 2 online is something you should try out to play with. It's super cool. So what we did, and I think this is just like the best demonstration of how a cryptographic hashing algorithm works and how we can use cryptography to later find consensus. This is like the foundation for all of this to work. So we use the same algorithm. We took your key, we specified all the parameters, and we generated this hash that says Zen11. And the miner continuously generates this random keys until you hit the one that makes Zen11 work. That's basically how it works. So without the key, you could just send any string with Zen11. But now your Zen11 string must match the private key, and this can be verified by anyone else. So that's how Argon 2 ID encryption works, and any type of encryption, really. This is just awesome tech that then enables us to build foundations and make immutable and secure systems. So this is crypto, guys. This is like what we are all about. But what does it have to do with Zen? So Argon 2 is, so what is Argon 2? I want to mention that too. It's a cryptographic hashing algorithm, it's called, specifically used. It was produced to hash passwords. So what Jack did was to figure out that we can use this hashing algorithm that's usually done with password and use as the proof of work that you as a miner use to find the correct solution, Zen11. So he thought there has to be algorithms that are resistant to ASICs and GPU, where I can do one-way hashes with a fraction of the cost of the hardware. So then he found this Argon 2. Because it's a bit disappointing with the Ethereum algorithm, with the transient GPUs and power hogs, because it makes everything hot. It's kind of old tech as well. It's like 8 years. So if Argon 2 works well, then what if we release a simple miner to try it out? So that's how it actually began. So you can read more about the Argon 2. But that's like how hashing works and what's happening with the proof of work when you mine XenBlocks. So let's go back to the school board. So that's the basic, that's the most important thing to understand. Like, what are you doing? Like, what are you doing with your life? So then there's also SuperBlocks. And what are SuperBlocks? So it's this exact same concept as finding Zen 11, except your string must contain 65 or more capitalized letter. So the difficulty of finding them is about 1 in 1,000, something like that, that you find XenBlocks. So, and why is this interesting? Because the first question that Jack had was, can we make a blockchain with proof of work, very simplified? And can we make them something that is very hard to get? And that's why we have SuperBlocks. So they occur in like 0.1% of the time. So if you look at all the blocks produced, what's the percentage of normal blocks versus XenBlocks versus SuperBlocks? I think it's pretty cool now because we get a lot of data with all of this, and we're going to look at those later. So SuperBlocks, it's like a token. And regular blocks can be used as gas, for instance, whereas SuperBlocks is like a scarce asset. It's very hard to get times 1,000, and just because you're searching for an extra thing with the hash, it's like merging Litecoin and Bitcoin at the same time, and then using Metamask signature with Ethereum. So we're going to talk about that now, because next he thought, okay, there should be an integration with what we're producing here with the wallet. So then we integrated Metamask just with the RPC server using Python just to connect to the leaderboard and read everyone's SuperBlocks. So x.blk is what its SuperBlocks is called. But let's see if this changes. We just yeah, I'll wait for that later. But the point is that a SuperBlock it's like a token, but it's not technically a token. So, you know, as you know, the ERC20 is the standard for tokens, but that came later. So first you had the Ethereum balance function that's returning sort of a SuperBlock, but it's not a contract. It's just a balance of your wallet. So SuperBlocks and blocks, they're just records. There's nothing in it. ETH is not an ERC20 token. It's just records. So that's why you need wrapped ETH to trade. So if you swap ETH through, it routes to wrapped ETH. And for limit orders, as you know, you have to wrap it first and use wrapped ETH. So if you want to trade on these on Uniswap, what could be done is you could send a transaction to the XenBlocks chain to validators who would give you permission to mint a SuperBlock on Ethereum, for instance. So the validators would then create a record on Ethereum to this ETH address that's specified, saying that this is allowed to trade this amount. So it's a immutable contract on Ethereum that can issue and burn a SuperBlock on Ethereum, you could say. And in Metamask, so you can add this XenBlock RPC ID. Sometimes it switches, so it becomes something else, but this is the right one that you need to use. So if you do it right now, connected to your Ethereum address, you will actually see something else, not SuperBlocks. You will see normal blocks, Xenium. We'll talk about that a bit later. And then we have Zuni. So what is Zuni? Zuni time, because an interesting method that you could use to mine a fungible token or non-fungible token with proof of work. So while the Argon 2 hash algorithm is looking for the Zen 11 hash, it simultaneously can look for other hashes, such as Zuni. And what makes Zuni special in particular, because the algorithm will always look for them, but you only find them within a certain time frame, when it's Zuni time. So that's when they will be valid to find. So Zuni time is every hour on top of the hour, so to speak. So it's 5 minutes before and 5 minutes after the zero. You can say it's top of the hour. So what you can do, like what this demonstrates, is that you can co-mine many tokens at once, and this is called merge mining. So you have your miner adjust to another search string, and it won't cost you basically more because you're using the same proof of work. So this can basically be proof of work tokens. You can mine for basically whatever. Here's actually a diagram of how much have been mined so far. I think Tree City West did. He's been working day and night with this project. It's been awesome to see. So here we can see regular blocks, SuperBlocks. We can see how hard them is to find, and then Zuni blocks. So it kind of makes sense. It kind of looks like an hourglass, actually, if you look at it like this. Yeah, it's actually perfect. So yeah. And what else? Leaderboard. So a leaderboard, if you go to this address, zenminer.move.com :4448-leaderboard, because there's different variations of it, you see this. So once your miner have found their hashes, they need somewhere to be able to see them. So Jack deployed this leaderboard, which is just database. It's a system that counts everyone's blocks. So on the leaderboard, we can see some interesting metrics as well. We can see total blocks made. We can see the mining block rate. This is very essential. We're going to talk about that. The current miners and the current difficulty. So miners are then ranked by how many blocks they have made. It's as simple as that. So it's basically like a mempool of just organized transactions, and that contains both confirmed and unconfirmed transactions. But we can visualize this on this leaderboard. Yes, and this is basically the basics, guys. What we just covered so far will get you like a long way to understand how all of this works. This is how you mine. This is we talked about Hashrate. We talked about XenBlocks. We talked about what we're actually looking for and how we can verify that it makes sense. SuperBlocks, Metamask integration, and yeah, Zuni and Leaderboard. So now we're going to be way more technical, and we're going to talk about fixed total or global hash rate and difficult adjustment mechanism. So what is this juicy stuff? The biggest difference with Bitcoin and this system is that with most proof of work miners, it works in the way that the more miners join, the more hash rate the system produces, so to speak. So as Bitcoin grows, the total hash rate will go up forever. With XenBlocks, we have the same global hash rate of 7 million hashes per second, or maybe you should say 7,000 kilo hash per second, but it doesn't matter. It's the same thing. So we have a fixed amount. So the global will always be this. So what we do is we reduce the hash rate for the individual miner when the difficulty increases. So for everyone, the difficulty got up, the individual hash rate is reduced. So it means that you will end up using less and less power the more miners join, instead of pushing it up to infinity. So we reduce everyone's hash rate instead of having this infinite increasing hash rate. And a few other systems do this, but not many. you don't like have to increase the hash rate. We can just split a fixed amount of hash rate among however many participants we have. So you will individually see a lower and lower hash rates produced as more miners join, which I think many of you have done already. That you're using the same machine, the same setup, but it's running slower, and that's because more miners have joined. Difficulty has increased, and you are producing less guesses per second. So older algorithms, they don't do this. With Bitcoin and Ethereum, for example, proof of work miners on Ethereum and Bitcoin, they can't be adjusted. They're not adjustable. You can't adjust the difficulty by changing the algorithm. They don't work like that. So here we have a global hash rate of 7 million hash per second, if we're allowed to say that. And to find one block, the network needs to go through 7 million hashes because we're making one block per second. That's how the system is set up. So your individual hash rate will adjust or drop down within this area. So with Bitcoin, it's 1 block per 10 minutes, as y'all know. So this means assuming that the network grows, and this is just a test, but who knows if people will continue to mine if they like it, then in a long time, you will make a very small amount of hashes per second. But now you can do quite a lot. So it's fair because it's the same for everyone. The only alpha you have with this system is that you can try to get cheaper CPUs servers and rent. But they're available everywhere. It's the most available. You have CPUs in everything, even fridges. So the way this works technically is now with the difficulty adjustment mechanism. I love to say that word. Difficulty adjustment mechanism. So if you saw this hash rate, never mind it. It was wrong. It's actually 7,000 for as a total. And the way it looks, the way it works is because there's a difficulty adjustment mechanism built into the system. So we can see here on the leaderboard, we can also see the current difficulty, and this is an important metric to follow, because the system is set to give around 1 block per second, so that's 60 blocks per minute, and that's roughly 85,000 blocks per day. So the difficulty adjuster is running and managing how quickly you can get these blocks. So the blocks need to have some sort of scarcity. So the rate of blocks is then set to be 1 per second, not more than that. So when there's more miners and the difficulty is high, the wattages increased, or they are instructed to be lower on your CPU, which is cool because it's usually the other way around. So with Bitcoin, the difficulty is just how complex the hash you're doing a match for, not how much memory you're using. So the difficulty adjustment, the difficulty manager built in wants to keep this total hash rate of 7,000 kilo hash per second. And this will adjust everyone's mining to make it more difficult to maintain that peg of 7,000. And it will get more difficult as more miners join, and more easy if people start mining. So the way it's programmed is this. It's 60, the hash rate or the block rate is 60 per minute. So if the block rate goes up, if more miners come, if it goes up to 20%, up to 72, nothing happens. But if it goes over 72, the difficulty adds 100, which makes the block rate go down. So the difficulty increases, the hash goes down for everyone, and then the mining block rate goes down back to 60. So the difficulty will start dropping, then 20%. If it drops more than 20%, if there's less miners, down to 48, the difficulty will reduce by 100 as well. So and it goes on like this in this cycle. So it stays within this this interval of it tries to be 60, but if more miners come, the hash rate increases, then it will increase the difficulty. And if less miners are hashing, then it will decrease the difficulty. So it's an adjustment mechanism, which is pretty cool. And if you go to Jack's directory, if you like this when a nerd, you can just go and see the code that I just explained exactly how it works. And here you can see the block rate, how it's ever changing with all the blocks when we mine. So it stays within this interval of here it went up to 73, so then it's gonna try to push down a bit. Are you following me so long, guys? Because yeah, this is also interesting with this, because here's some screenshots from Jack's computer with like this CPU offloading, you can say. Because the higher the difficulty, the slower your CPU is working. And when the difficulty increases, your temperature on your computer actually drops. So it's ESG compliant, you can say. And ESG is just a big scam. But how so? Because I was thinking, how is this possible? Because you're still mining at full CPU. So full on work at all times, you should have a constant high temperature. But what happens here is you actually load your memory more, and memory takes less watts than CPU. So it takes 1 watt, and CPU is like 300. So the higher the difficulty leads to offloading to memory more, and memory takes 1/300 watts. So the CPU is working less, but it can't go fast due to memory being slower. So what is actually offloading? It's offloading the hash calculations, and memory can't do those as well. So you basically put a giant data structure into RAM to make hashing slow. So it's part of protection for making hashing too quick for passwords. So this was the algo used for passwords, Argon 2. So that's how it was repurposed for this instead. So that's just an interesting side note for all the hashheads who are talking about this in the chats. When it comes to GPU miners, let's also talk about that, because Argon 2 is ASIC resistant. Like, you can't use an ASIC with it, but it's not entirely GPU resistant. Woody in the chats know all about this. I've been seeing him doing some tests with GPUs. It's pretty cool. So Jack also tested the code. He rented $1 per hour GPU and was able to get 50,000 hashes per second. So you can rent a GPU for $1 per hour, which is expensive. In a month, that's $700. So if $700 produce 50K hash per second, but if you instead rent a CPU, like a Ryzen 7900, I've rented a lot of those. I think they work fine. They can produce around 30,000 hashes. So you have 30,000 versus 50,000. So it's almost it's almost the double with a GPU, but you pay 5 times more for the GPU. So at the moment to test at what we've been testing GPU so far, the cost per hash is about 2.5 times as expensive as CPU. So if you pay $1 per hash for CPU, you would pay $2.5 per hash with the GPU. So it doesn't make sense. So even though it's faster, it will cost you more. And so it makes more sense to rent a CPU because you will get more hashes per second per your dollar spent. Yeah, so you can't outcompete you can outcompete a GPU by getting more CPU servers, basically. So it's at this point, it is possible that maybe old GPUs can outperform new and expensive CPUs, but you'll have to find the right one that'll work for you. So that would be interesting to actually, if people wanna study it. So high-end GPUs that's expensive doesn't make sense to mine with, we think. But maybe old ones that cost less and are faster and more cost efficient. So if you have a slow CPU at home and then you find an old GPU, you can get it faster, but you can't build a GPU farm and get more hashes per dollar spent. Yeah, so that was just super nerdy, I know, but yeah. So we talked about fixed total hash rate, difficulty adjustment mechanism, and this is something that separates this system from for instance, Bitcoin mining. And what else? Yes, let's talk about mempool, blockchain, the state, and sync node, how they all fit together. So how do we make a blockchain out of this proof of work? Like, how does this all relate? So miners mine blocks. They're using the same cryptographic hash algorithm, Argon2, to make it fair, following the same rules. So they create XenBlocks and SuperBlocks and Sunnis. So the leaderboard is acting like a visualizer of the state, you can say, including the mempool. So giving you all the transactions that has happened, whereas all haven't yet been inserted into a chain. So the leaderboard stores basically everyone's transaction. And the transaction is when you found the block, what we call the XenBlock. It's a transaction. So the leaderboard is fetching this data from the mempool, from blockchain DB, which is the state. So the state is basically the whole chain, the whole hashed, Merkleized, rooted result of the whole chain, which you can copy and share and whatever. You have the whole chain in this database. And the mempool is just unconfirmed and organized transactions. So the mempool shows the unconfirmed state, you can say. Unconfirmed meaning that it hasn't been built into a blockchain yet. So there's a bunch of unconfirmed transactions ready to be committed to the blockchain. So when nodes run sync node, this script that's in the directory as well, they fetch all the transactions, they verify them, and it builds the blockchain. So when nodes run sync node, that's basically construction of the chain, you can say. So mempool is a database, but you can also think of it like it's a smart contract that has all the logic in terms of how rewards are created. And like we have three rewards right now, like Zen11, SuperBlocks, and Sunni. So the smart contract accounts for all those rewards, and sync node makes it into a blockchain. So if the smart contract is compromised, none of the rewards would work. But since you have the blockchain synced amongst all the different various nodes, then it becomes immutable. So once you run sync node and you have many nodes, that can't be changed. We're going to talk about how that works, because it's been synced with many nodes already. So historic data can't be changed anymore, and that's what makes it immutable. So we're going to go into exactly how that works. And there's then copies everywhere that miners and validators agree on. So once we get the state where nodes also sync, once we get to the state where nodes also can sync peer-to-peer, then we have a really immutable change, and we wouldn't have to talk to the leaderboard at all, because then we can intercommunicate. So right now the mechanics of the function behind this can be altered a little bit, and it's needed since we're still building the logic for it. But the rules for what the system should follow is something that need to be like customized. So, but sync node is already up and running right now. So if anyone tries to manipulate it, the network that we have already now will pick up on it, and we can tell what's not working. So blocks are already Merkleized, and we're going to talk more about that soon. So yeah, right now there's still things that can be adjusted, but when we can have sync node intercommunicating peer-to-peer, it will be super difficult to do that. So just one more thing about this, like the leaderboard is showing also unconfirmed, but the time aspect of this, it's showing the unconfirmed last 60 seconds worth of blocks mined. So it takes about a minute to finality. To actually confirm takes just seconds. So there's confirmation, which is first, and then there's finality, which is after a number of votes, which is usually a majority. So confirmation and finality are two different things. The leaderboard is showing the blockchain database, and most is basically confirmed transaction, because after a minute they will definitely be so, because we have 1 second blocks and they're coming at a speed of 60 per minute, so 1 per second. But you need 100 blocks to make a sealed block. I'm going to talk about that next. So it's almost, to be really precise, you need 100 seconds. That's 1 minute 40 seconds to get the correct state. But transactions can also fill very quickly. So in this 100 per sealed block, it's just it's also something we can change. But anyway, yeah, forget about that. Also, what needs to be done here, which is a thing you need to add, is which all chains has, is and this we don't have right now, is the one who pays most gas is chosen first. So that part needs to be written somehow. That's the standard way. Bitcoin has fees, Ethereum has gas, so bidding actually to be included in the next block. So that's something that needs to be added. But that's just how like things are like working in conjunction with each other, because you're going to hear all of this sync node and blockchain DB and leaderboard and transactions and where are they, whatnot. So yeah. It can be good to see how they relate. So let's talk about the process, how it actually works. So the miners, they generate the SAM block, and that transaction goes into the mempool. So a bunch of transactions are already committed to the blockchain, but by definition, the mempool doesn't have any security in it. It's just a bunch of transactions. So the mempool waits for 100 XenBlocks to come in, and it creates a so-called sealed block from those 100 XenBlocks. So every sealed block has 100 XenBlocks, and they generate 1 Merkle root for that sealed block, so it can't be altered. I'm going to talk about what Merkle roots are. So the Merkle root hash is what we see in the block when we find one. You see it here. We didn't talk about this, but by the way, status code 200 means that everything is all right. If it's 400, it's there's something wrong with you, or not wrong with you, but the way you mine. But anyway, here's the proof of work successful, record stored successfully, the block ID, and here's the Merkle root. Bam, 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 bam. You probably need to see the stream one more time if you're super confused right now, after you played with it in a week or so, because then you're gonna want this structure, how it all relates. But if you're listening to this for the first time, I feel you. It must be super frustrating, but it's good. So yeah. Where were we? It creates and then that goes to sync node. So sync node is the greatest. So with sync node, that's how we make sure to decentralize the chain and cockblock when needed. So sync node downloads this sealed block, you can say, the last one from the mempool. So every transaction is defined, it has the keys, it has the parameters, it runs verification on the sealed block. And once it verifies the transaction, it says, I will generate a Merkle root. So many miners do the same thing. They all download the last sealed block and so on. So what you can do, you can run sync node as I showed you. You just do Python or Python 3 sync node pi and then your address, and then you're doing basically this whole process. You're taking the sealed blocks and making Merkle roots with them. Yeah, like we did here. Block Bamba is valid, computed Merkle root match the stored Merkle root. Bam, bam, bam. So and when we have enough miners who all do this, we can run consensus, and we can talk about things that will make you incentivized to do so in a bit. Also, so the yeah. Then that goes into that, like builds the chain. So the IDs, these Merkle root IDs, are then inserted into the blockchain DB, the database. So with the Merkle hashes. So a Merkle hash is a signature of a sealed block. If a sealed block is altered in any way, the Merkle hash is also altered, and validators will find out. So I will talk about that. So yeah. What else? I've written down things I need to say because there's so many. Yeah, exactly. So when everyone can send mind blocks to anyone they want, we have a truly peer-to-peer network, which is the end goal. So blockchain DB is the chain. It's a full set of the chain. It's the state. You can copy it and you can share it. So the chain, what is a blockchain? It's just an immutable data structure. That's all it is. It's just a ledger that people can't alter. And this is what blockchains really are. Just like Bitcoin, it's an immutable, unalterable. We learn new words. Here it's education. Unalterable word, ledger. Yeah. Anyway, so yes, and then we also have block voting, which is pretty cool. So what is block voting? So block voting, it's so here you can see the ID. You have the block Merkle hash. And you have the last numbers is how many votes it got by the miners. So one vote is one miner finding a block and then verifying other blocks. So every time they find a block, they also do voting. And those votes show basically accuracy, like how much we can trust this Merkle roots, because 28 others have verified this and that it looks fine. So we want this number to be as much as possible. It's like a social work score. ESG compliant. Anyway, so once you mine your block, you verify 100 others before you and cast your vote. So it's built into the mining exercise. So the state records your ETH address that it's verified 100 blocks every time it mines a block. And then the score is how many times this has happened. And the hash is a Merkle root of a block with 100 records. But number of votes is how many ETH addresses miners voted the same. Yeah. So there's no voting. Like if the data is correct, it's correct. But it's just a measure of how many are how many have ensured that the calculations are kosher. for instance. So every miner that run an updated code votes on blocks having the same Merkle root hash, and everyone who has a copy of the same blockchain .db, because they can then compare their hashes. So the validators could act as an authority for blockchain, for the state, basically, in creation and validations. Then you, for example, stake your SuperBlocks, and now you have authority to broadcast. So we'll talk about that later. Like I am a staker, therefore you should trust me, because if any of the stakes are malicious, then other stakers will reject me, and I will get slashed or whatever. But that we can talk about, and this is when it's interesting how we can combine like proof of work and proof of stake. So here we can see, here's a later screenshot of block voting, and here we can see that the sync noders are getting stronger. Okay, so here someone says, I'm hoping to figure out how to mine this. So don't listen to me now, like with all of this. This is just how you want to understand. You don't need to understand all of this to start mining. But if you want to understand how it all works, this is like the things you need to know. But I would just suggest stay in your mining bubble and play with these things, like first for a few days or for a week, like just to get up and running. You need to master this part. This is your first mission, Xinian. This is, if you master this steps, you become a Hashrate. Anyway. So block voted terminology. So let's be clear, guys. Let's be clear here. XenBlocks, it's not a blockchain block, just to be perfectly clear on that. So XenBlocks is like a transaction, and Bitcoin works the same way. You find the block and you submit the transaction to the chain. You just include other transactions that are not the blocks. So finding a XenBlock is a transaction. It's a record, and then you make a sealed block that then combines all the proof of work of many others. We call them XenBlock. So Bitcoin, when you find the block, it gets verified. Then you get your reward. But Jack thought that we switch it. We switch it on them. So you get one block reward for one block found instead. So we could have said that you find a block and then you will get this kind of reward, which we actually are doing now. I'm going to talk about that. But if we call them anything but XenBlocks, it would make less sense, because what this actually is the currency. So you're finding a block and getting a block for it is much more complicated to explain. So the reward is numerated in XenBlocks as a foundation, but then we converted this to Xenium. So it's kind of reverse, because miners don't make the blocks, they create the currency, and the sync node runners are the validators. So what we can introduce is them. If you're malicious, the network takes your staked XenBlocks or SuperBlocks and do some kind of slashing. So validators, what they have to do, they have to mine first, they have to sync the chain, they have to stake something, SuperBlocks or normal blocks or Xenium, and take away some balance if you deliver the wrong information. But just to be clear with the terminology, because that can be a bit confusing, maybe. But we just decided to introduce a Xenium. So what is Xenium? It's a pretty cool name, Xenium, XNM. And so one XenBlock found is 10 XNM. So if you connect your Metamask right now, you will see and have found blocks, you will see XNM in your wallet right now. Augmented, big shout out. I saw this. I thought it was cool. People are creating awesome stuff. The Telegram is awesome, guys. You have to join if you haven't already. It's just super awesome. People are going nuts. So yeah. And the reason to do this is important to understand, is because if we had kept it like this, we couldn't play with the proof of stake model later. And the reason is, if we can convert this to Xenium, we can add other logic that will help secure the chain. Because if you, for instance, stake XNM, we can build in a logic that you will also get more XNM. So like validator stake, you want to give them like 1.5 coins per block they found because they are stakers. So stakers will earn more because they stake. And so it makes more sense to have coins as reward for a block in that aspect. And then, yeah, I drew this, but then this is better. There was some talk in the community about halvening to build that in as well, because it would make sense. Like Bitcoin has 4-year halvening for block rewards. So we could have, for instance, first year you have 10 blocks. So that would be in total, because there's one per second. So that would be 310 million, and then a yearly halving, basically. So some kind of logic for that. So that's what's being talked about and iterated right now. So then you basically have the basic features built in. Merkle trees. I've been talking about them here when I talked about that the sync node creates Merkle trees of the sealed blocks, etc. And with Bitcoin, how you make the blocks immutable with SHA-256. You're also using Merkle tech. So Merkle trees, it's not Angela Merkel who became with the blockchain. She's still trembling somewhere. Merkle trees is it finishes the immutability aspect of it, you can say, because of all the blocks and transactions within a block, they are all hashed together, and they're following the original Bitcoin convention, where all the blocks are merged together into a chain, and you can't change any of the transaction. So let me just read the definition of Merkle trees also. So Merkle tree totals all transactions in a block and generates a digital fingerprint of the entire set of operations, allowing the user to verify whether it includes a transaction in the block. Verify the accuracy of the data. This method can be used to verify the data's accuracy successfully. Compared to other data structures, the Merkle tree data structure consumes extremely little disk space and may be broken into tiny bits of data for network verification. Merkle trees are used in distributed systems for efficient data verification. They are efficient because they use hashes instead of full files. Hashes are ways of encoding files that are much smaller than the actual file itself. Currently, their main use are in peer-to-peer networks such as Store Bitcoin and get XenBlocks. So, and the way it works is this. So you have you're creating a Merkle tree. So you have a block and another block, and they get a hash and another hash, and those two hashes are then merged together to another hash. And then it comes up to a Merkle root hash up here, and the same thing goes on in parallel over here as well. So and you call these leaves, and this is the root, basically. So yeah. So if you have a sealed block of 100 blocks, which you can see as leaves, you can match any transaction within that block and get that Merkle tree hash. So it basically says, if I mined a lot, and if I say that I mined a lot, and someone says, No, you didn't mine that much at all. You know, you can't modify the block here. The block will no longer match this hash. So if you try to change anything here, this Merkle root will match and will change. So then you will see that there's a discrepancy right there. So it's basically how you can, it's the process of how you make the chain immutable with Merkle roots. So yeah. Oh yeah, here we can see. So in our case, we have it like this. So we have the records. We have 100 SuperBlocks mined, and we want to make them immutable. So sync node makes them come into a sealed block, and there it creates this Merkle hash. It's called Merkleization, and this then goes to so Merkleization is happening with the signature of the sealed block with sync node. So you have, and then that goes into the blockchain database to become a block. But then there's also Merkle happening here. So you have with the SHA-256 method. So you have a sealed block and then another sealed block, etc., etc. So the hash of this block, this is how SHA-256 works. The hash of this block and the hash of this block creates another hash and creates this tree right here as well. This is called Merkleization, but this is not called Merkleization. So you basically you hash the Merkle roots together. This has a Merkle root, this is a Merkle root, and you hash them together, and you go on. So this hash sealed block 3 comes over here, and then you hash that block with the hash of those 2 blocks, etc., etc. So it goes on in this perpetuity. So Merkle tree, a Merkle tree binary, a binary Merkle tree is being built. Yeah. So here's also an animation. You can see how it works when it builds this tree. So it has one block and then another block, and it creates this this hash. So if we have, in our case, for instance, we have 100 blocks. They connect and make 50 branches. So 100 SuperBlocks become 50 hashes, and then 50 is split to 25, and 25 into 13, and then 13 you can't split it up, right? You can't have half. So you can't have half of a hash. So you also make a copy of the last one. We can see it here in the animation. Yeah. And then 13 becomes 7, and 7 becomes 4, and 4, 2, and 2, 1, etc. So that's how you build the Merkle tree. So you have the Merkle root, the signature of the sealed block, Merkleization, and then to build a blockchain, all blocks has the who has the Merkle root hashes. They are then also they need to be in sequence. So they then create the blockchain, and SHA-256 is the hashing part. But building the Merkle tree is the data structure part. So yeah, that's very important. All right. Proof of work versus proof of stake. How are you doing, guys? Are you still with me? All right. So I want to talk a little bit about like the differences really between proof of work and proof of stake as well. because this I derived from a stream with Charles Hoskinson. He made 2 streams that I think everyone should watch. If you just search proof of work versus proof of stake, I think it's well worth to watch them if you haven't already. Like proof of work versus proof of stake, and also resources, hybrid consensus, 1-to-n. I'm just gonna recap the most important thing of it, because he makes a couple of interesting points that are interesting to understand, because what he brings up, and as he said, the engine of cryptocurrencies is to the thing that makes cryptos transform is going from one state to the next, and so on, and find and the thing that makes them do that, the engine of that, is the consensus algorithm. So you have this big decentralized mesh of nodes and connection and transactions that are occurring all the time, and information is flowing constantly. So the challenge is to order them something in a meaningful way, and this is a problem even before blockchains and Bitcoin. How to find consensus in what happened when, where, basically. So using proof of work, that's just an engine that basically allows us to make decisions of who gets to decide the serialization for that moment, to update the system, that block, the heartbeat of blockchain as a block. So every time a block comes, the transaction needs to get proved, and proof of work is just an engine. So there's basically 3 things that need to happen. You need to pick someone to make a block, you need to make a block and distribute it, and the network needs to accept the block. But with proof of work and proof of stake, these are basically more or less fundamentally the same. The main difference between proof of work and proof of stake is how do you pick someone to make a block? And with proof of work, so he builds this whole case with proof of work that it's built with ASICs, just FYI. But we don't really. I'm not going to go through all of this. It's better you listen. But I'm just going to make the main points. So he makes this main point with proof of work being with ASICs, but we have ASIC resistant proof of work, so it's a bit different. But the important thing to know that this proof of work, it's an external resource. It's not inherent within Bitcoin itself. So you solve this cryptographic puzzle, and if there's a total hash rate of this, and you have 10% of that, then you are in 10% of the cases, on average, are going to be selected to be the one who submit the block. The way proof of stake differs is in this part, how you pick someone to make the block. And what proof of stake needs to do instead is they need to invent this synthetic resource. So if you have 10% of the synthetic resources on average, then your expected value should be 10%, where you get to be the dealer. So in proof of stake, instead of miners compete against each other, they are required to lock up some of their coins as stakes. A validator is chosen at random to validate the block depending on his stake weight, how many coins he staked. So to synthesize this process that we can do with proof of work with hashing is very complicated. So the question with the synthetic resource is it fair and is it secure? And he talks about synchronous, asynchronous, Byzantine actor allowance, like how many, what's the rate you want to allow, attack recovery system, randomness. It's super interesting. I think you should watch it. But with proof of work, you get all of this more or less very well. So to do this with proof of stake is pretty much non-trivial. He also talks about this, like these systems, it's like an engine, and I love machines. So I think this is a good way to look at these systems as well, because to compare different systems, we can look at them as an engine, because you have throughput, so that's how much material can pass through a certain width in time. And we measure it in TPS. So we can do this both for proof of work and proof of stake systems. You have a latency, which means how long that takes, and you have capacity. So for instance, with Bitcoin, you have 4 megabit blocks. Like how much data can you fit within your engine, in your process? Now, and then you have transactional properties, which differ a lot as well with proof of work and proof of stake. But the main thing, how to view these different stuff for the engine, is which resource are you feeding your engine with? And this is where it talks about when it comes to someone picking the block, how you pick someone in charge. With proof of work, you have the hash rate, how many hashes per second you can do. And with proof of stake, it's the ownership of the asset. So again, if you control 10% of the total amount of hashes produced, you will be selected in charge 10% of the time. And with proof of stake, if you own 10% of the system, you will be selected 10% of the time. But the point is, these are just resources. And he talks about that you can combine these together. So he talks about how you can go from 1 to 2 resources and eventually 1 to n. So you have a slot here of block 1, block 2, block 3. The question is, who's going to make this next block? And how do you decide this? You can choose just to go with one model, or you can have a pool of many different choices to go from. And I think he brings up a valid point, because why should we even ask that? It's because you're making assumptions with proof of work. The availability of ASICs, energy cost, knowledge, geographical, jurisdictional conditions. But you're making assumption with proof of stake as well. Ability to acquire the token and stake it. You need markets that are decentralized and censorship resistant. There have to be a seller for every buyer, etc., etc. And there's not only proof of work and proof of stake systems. There's also proof of merit, proof of storage, proof of participation, and stuff like that. It's interesting, because I bring this up for you guys just to know that there's a lot of when it comes to finding consensus in a system, how you're going to create a block and how you're going to distribute it and find consensus on it. There's a lot of different models out there, or researchers who are studying how you can make this work in a game theoretical way. With Fastnet and X1, I don't think we're gonna change the model there. It is a proof of stake systems, but that's why it's also awesome that we have a proof of work environment. If there's, because I don't think we should neglect proof of work completely. If we can make it more efficient, there's a lot of value to have that as well. But it's cool that you can make a hybrid of it by stitching all of these resources together. But then it's a big challenge of how you do that, basically. So just a little recap that it can be done, and it has been done in various cases. But when it comes to, and this is interesting, what we're thinking with XenBlocks is to make another kind of proof of work, proof of stake hybrid. So if you're comparing proof of work and proof of stake, you might say like proof of, you can't say that one is better than the other, because it totally depends on what your use case is. So anyone who says that one is better than the other it's just different system. That's what I will make. But if you say that like proof of stake is better because it's affordable, it makes the network faster, etc. You can also say that proof of stake's problem is that if you have a lot of money, you can then corner the market because you can have as many validators as you want. So for proof of work block creation, it's the part here when it comes to choosing the one who's going to do the block, it's much superior in a way, because you have all of these things that you need to solve in a secure way. So Cardano did this with Ouroboros, for instance. and it might work very well, but it's also makes it incredibly complex. So what we thought with XenBlocks instead is, if you mint to get your currency, and then you do proof of stake to stake it. So then you're not bringing any outside capital to stake the network, and it gets better. So one could argue, and that would create a hybrid solution, because the only way to decentralize is to give rewards to people who validate securely. And for that to happen, the chain needs to be decentralized on people's servers. So what we could have is proof of work when it comes to ASIC resistant CPU mining. And the resource then is hashing. So it's kind of like gas mining, because what you're mining is currency. And then you use proof of stake. So the resource there is then the ownership of the asset. And you stake by block voting, by having a copy of the blockchain, and by staking XenBlocks or SuperBlocks or Xenium. And you can have some kind of staking incentive that you get the 2x the block rewards if you do so, or whatever. So it becomes sort of a meritocracy as well. And then you get chain validation. So it's kind of reversed in the sense that miners don't make the blocks, they create the currency. And the sync node is the greatest. They are the validators. So and if there's something that's being maliciously done here, then you could have some kind of slashing happen, for instance. So finding blocks is the currency, building blocks is the validation. This is an interesting model. Because if you have a proof of stake model, you then have the choice. Like, a miner can either sell or you can stake it with rewards. So you have an incentive not to sell your staked rewards, which is with Bitcoin, you don't have this inherently. So miners do sell because they have an upfront cost. So they at least sell a little bit. Either they're a holder or you're a member of a cult or you sell. So you still need to sell some of your XenBlocks or Xenium to pay for your upfront cost of your cost of CPUs, but you also have a financial incentive to stake them, which contributes to the security of the network. So yeah, I think this model is pretty interesting to try out for this system. So it's sort of like interoperability between proof of work and EVM, because proof of work is the gas mining. You then use your gas for transactions. And if we are EVM compatible, which we can easily be, then you can do everything that EVM can do, but with the gas token that is XenBlocks. So we could mine. It would be interesting to mine Xen using XenBlocks or Xenium as the gas token, for instance. So there's interesting things that could be done, and then integrate that into X1 somehow. So I mean, to be honest, there's basically two problems with Bitcoin, in the sense that you, like 40% or something like that, the miners, they're ASICs, and it creates this oligarchy of miners. And then you have BlackRock buying ownership of the miners as well. So it's and that's number one. Number two is that they don't have a direct incentive, but then to sell on the market. So yeah, the Bitcoin didn't implement all of this. It was like super hard to it's super hard to make any changes to Bitcoin, of course, but that's a feature or a bug. But it would be interesting in this model to implement proof of stake with the gas mine token as the resource you use to stake with to further secure the network. Because mining, it solves a lot of problem. Like if you want to simplify blockchain, that mining part makes it like super much easier. And you don't, because you don't have to fairly select who gets the reward. And you just need to be a miner that stakes, and it reduces the need to dump, basically. So yeah. So this project is pretty cool because it's like being in Satoshi, the Satoshi group from the early days, how to figure out how to build all of these systems in a new way. But now we have all this knowledge from 14 years of empirical tests and research that we can just pick and choose whatever has worked very well. So that's it, guys. I also want to mention community. Guys, it's been so fun to see. It's been like amazing to see all of the community participation in all of this. Like the Telegram group has just been exploding. People are sharing, they're building rigs, they're playing, they're ordering different CPUs from different server. They're ordering servers with different CPUs, and they're building rigs, and they're trying out stuff. Here's Jack from this data rig that he built in Google. So he has a lot of experience in this hardware section of crypto and scalable systems as well. So that's also pretty cool. Here's someone that built a that has a, I think this is a GPU rig that he said, if we're ever gonna do it, I'm ready. Guys, it's just been awesome to see people sharing their stories. And oh yes, Joseph, we're going to talk about Joseph too. And he hasn't slept anything. I thought this was pretty funny. A guy was trying to buy some. Is the whole setup you're selling? And he says it's graphic card only, as in the ad title. Okay, I thought it was the whole PC. How much for the whole PC? I don't sell the whole PC, just a card. Okay, can you sell me a space on your PC for crypto mining activity? I'll pay you $50 a month for your service. It's incredible. So like just within, I think this is the power of our community, that we within, and Tree City West also built an explorer that is super cool. So you from the terminal can access the whole chain, which is just super awesome. But I think this is like the strength of our community, that we can merge the community participation in our research to play with all this stuff. And now we have this whole proof of work community, which is just super nerdy about all of this stuff, and we're sharing and we're trying to figure out what's the best setups and how to mine this in the best way. I even mined when I was going to the airport, like in the middle of the chain before the Wi-Fi ended. I wanted to continue mine. So it's just been super fun, and to play around with this stuff. I hear so many people who say, I have no idea how to mine or how to use terminal or how to use Python or whatever. And this is probably like the best way how you can learn how a blockchain works fundamentally, how you can learn to use terminal, command line, how you can learn to use open source systems like Linux, and how you can learn how to buy a server. Renting a server, if you've never done it, is pretty simple. Like CPUs, they're everywhere. You have to be careful because a lot of them have in their terms and conditions that they don't allow crypto mining for some stupid reason. But you can either think like, okay, I find another one, or it's easier to get forgiveness than permission. It's up to you. But it's you just have to sort of know what you're looking for. So go into Telegram and ask for advice. And then I rent which one do I have? A Ryzen. One that I think has worked very well for me in relation to cost. What is it here? This one, Ryzen 7900X, 12 core. I would like to get to 24, but I couldn't find it. So that's one example. And you just need to know what you find for, and then you basically rent it. You rent it monthly, and then you get a you pay like $150 per month or something like that, and then you get an IP address and a password, which is the thing you use to log into your terminal, and that's it. And when you rent it, you can also make sure that it has Ubuntu pre-installed. So then it's just like plug and play, basically. So if you have that set up, you rent a server, if you don't want to do it on your computer, because the computer CPU is going to eat quite a lot. So it's going to annoy you after a while. So you can just rent a server and mine XenBlocks from there. But in anyway, like the community aspect of this is just awesome. So it's pretty cool to see. I have a bunch of other stuff I could talk about, but I think this is enough, guys. So let's just do a recap of this. We talked about how to mine, and if you're new to this, yeah, I would just start there. Forget about everything else and just start mining, so you feel how it is and start playing around with stuff. We talked about Hashrate, the leaderboard, the difficulty adjustment mechanism. I hope it became clear for people how that works, and the difference we have towards, let's say, Bitcoin or Ethereum proof of work mining, in that there's a fixed hash rate for the global that's not working. So we basically share that hash power collectively. So if there's more miners, your CPU is going to work less. We talked about mempool and the state and sync node and the process and block voting, some terminology. We mentioned Xenium, Merkle trees, how that works, proof of work, proof of stake. What really is the main difference? If you simplify it, and we have to simplify things, it's really in the first step. Like, how do you choose someone to make the block? And with proof of work, you're doing this hashing, this guessing. Whereas with proof of stake, you have to sort of synthetically come up with a system that's secure and fair to make an equivalent of that, which makes it super complicated. But of course, it works. Ethereum moved from proof of work to proof of stake. Cardano is proof of stake. And most of the EVMs that we are on are also proof of stake. So, and then we talked about that you can. There's research going on how you can have a mix of these resources going into that picking part. But what we are inclined with this is to merge proof of work and proof of stake in another way. So you have the proof of work as getting the currency and then using that currency to stake to incentivize security of the network. So let's fucking hash, guys. Let's fucking hash. Lick the toad. It's like mining Dodge all over again. Yes, I mean, it's super fun because it's something more tangible with mining, mining with proof of work. It's something to work with, and there's a lot of things you can optimize and play with, and people have and people do. So yeah, I think it's as an educational project, which also helps us to optimize X1. This is just awesome project. But start mining, get in there, get your hands dirty, play around with it, learn a little bit about what Hashrate is, try this Argon 2 hash generator. When you find a block, you go there and you test it so you can see that it actually works. Go to the leaderboard and understand that there's difficulty adjustment mechanism. So the higher number this is, basically the harder it will be for you to mine. And like you want this number to be high if you want a strong chain in the long run. And yes, try to get familiar a little bit how these things work together. And once you learn how to mine, try to also run sync node. So sync node, in your terminal, you basically just use this command. And that's why it's super simple too. Like you can really feel like Neo, and just using these commands. And just because that, now I don't find it. Oh, here we go. So in your terminal, you just basically do this. You enter Python or Python 3 sync node, and then you add your address. And then it will start syncing. How does it look like? Oh, look at this. We found, I forgot that I mined. Why is the RPC, you do this one. It should work. It will work. Why is it not HTTPS? I'm not sure about. No, that was not BAO. Oh, I'm so tired. This chain ID changes for some reason. I actually don't know. But force it with this. And if you already have, then go into settings and change the currency symbol to XNM instead, Xenium. So you used to have SuperBlocks there, but we changed it. So now you have your blocks instead, but not your blocks, your regular blocks. It's Xenium. So for each block you find, you get 10 Xenium. Oh, yeah, it's Sunni time. Let's check. Let's check. It's Sunni time. Look. Simple waters. Yes, I will. So now it's Sunni time. Very exciting. Very exciting. So now we find Sunni. So as you remembered, I started my my miner here, full on force, and you know all of these things now, guys. So if you just press enter, you can see the current hashes per second, which has reduced quite a lot. But here we can say we found a valid hash with target SUNY after this how many attempts, hash to verify, Argon 2, you know this, guys, you know this now, you know what this means. The difficulty, which was, this is the hash that we found, and we should have SUNY here. There we have it. There we have it. See it? The key. So you go into Argon 2 hash generator and you verify that the system really works, that it's not trying to fool you. And we can see that status code 200, so that's okay. And that the hash verified successfully in the block saved. And then it goes on to mine the next one. So yeah, it's pretty cool. How do I see all the miners mining on the same terminal? So when Senzu time, now it's Senzu time. What I do is there's what you can do is just open many different terminals. 3City West had some cool feature where I think you could see many terminals at once mining. But I actually don't know how to do that. Let's look at our, so I'm gonna open up another, I'm gonna show you one more trick. So what, okay, let me just log into this server. So what we need to do is, first of all, we can just check the top, and here we can see all the instances it's mining on and the CPU percentage, and yeah, HTOP as well. I showed you that. So you can see it's pretty much maxed out. Another thing that's good to know is if you wanna kill all the miners, you can just use this command, pkill, and it will stop everything. Sorry, this won't work because we're not in the directory, so we need to go into some miner first. Bam, and then pkill Python 3. Bam, and if we now go to top, you can see that they all stopped. So another thing you can do is so the baseline is like this, that you can go to Python 3 and then miner.py. So that will start just like the miner. I'm just pressing enter, so I just want to see what the hash rate is. But what we can do also is use this command, this no-hub Python 3 miner.py end, because what that does is it starts the miner, and even if I shut down this terminal right now, the miner is going to continue in the background. So that's pretty cool. And if we want to see what goes on, we can use this command tail, and then we can see it. So it's tail. Let me post this in. Just some cool commands you can play around with. The very first step to become a hash head, you need to just you need to do this whole setup, and then you just start the miner like that. But then you can use this command to make it running like permanently, even if you close the terminal. And then it's not going to show anything. So then you type in this to see what you're mining. Also, if you just want to smack a boom and go on, you have to figure out how many instances you can mine on. Then you can do this also. So it basically says like it's a for loop, like from 1 to 24, do this miner, and that will start 24 of them, and then the same to it's a separate command then to show it. I will just like full force. How to see the hash rate? You could see it in the terminal. Oh, that was the one we killed. Is it this? Here you see the hash rate. Yeah, guys. Any questions? Go into the Telegram. What's the Telegram? XenBlocks. Uh, 1,500 hash heads. All right, guys. Awesome. A lot of fun with this. I hope I didn't complicate things. That you thank you. That you learned something and that you find this interesting. This is an educational project. We're learning a lot. We're doing it together, and it's super fun. Take care of your sleep. It's super addicting, and try to get some Sunnis when it's Sunni time. So that's it. Let me know in the Telegram if there's anything that was wrong or something like that. Yeah. All right. Over and out. Hash heads. Goodbye, goodbye, goodbye.